When we have an electrical circuit, Ohm's law gives us a relationship between the current, resistance, and voltage. And it says that I is V over R. We would like to find the rate of change of the current at t equals 1. And because we're given a specific time, it's really saying an instantaneous rate of change. Okay, so the first thing we can do is we can write the current as a function of time. Maybe I'll do that in blue. So the current, I'll do it over here, as a function of time is, we take V over R. Okay, so if we want to find the instantaneous rate of change of this function, this is a quotient rule. So we take the derivative, I prime of t. Well, we have denominator times derivative of the numerator minus the numerator times derivative of the denominator all over denominator minus squared. Okay, this is pretty good, but we always want to simplify only as much as we need to for a given problem. To evaluate out 1, which is what this is asking for, I don't necessarily need to simplify, but this one really is not too bad at all to simplify because you notice both of these terms have a 2t minus 2. And then we will see what's left. If I factor that out of both terms in the numerator, okay, so what's left is not that much. You see here we have a t squared and a minus t squared. That adds to 0. And then we would have a minus 2t and a minus makes a plus 2t. That again would add to 0. We have a minus 3, no, excuse me, a plus 3 and a minus 11. So all we're left with, in fact, I don't need this big parentheses, is just 3 minus 11. Okay, so this is our derivative. And you could simplify further by distributing the minus 8 if you would like. Now, let's, so this is the derivative as a function. This function gives us the instantaneous rate of change. It was a quotient rule. Now let's finish the problem. So we evaluate the derivative at 1. That gives us the rate of change at time t equals 1. And you see we get, well, this is 2 minus 2 times negative 8 over, and then something, well, maybe I'll fill in some of the details. Minus 2 plus 3 squared. You could figure out what number this is if you want, but you notice 2 minus 2 is 0. You know, times minus 8, 0. The numerator is 0, so you see the derivative, the rate of change at t equals 1, 0. Let's do another problem from circuits, and this one, if you sort of look at how long it takes to write, it looks intimidating, but it's really not too bad if we figure out everything that we're given and what we're trying to show. So, P is the power lost, R is resistance, and then I is the current. And we are told some things. In particular, right here, we see that resistance is a constant. So I can write the power lost, P, in the form 8I squared, okay? But I is not a constant. I is changing with time, as we can see if we continue to read. The current is increasing at a rate of 5 amps per second. Okay, this says, and this is all still what we're given, that di dt is 5. And then finally, what do we want? want the rate of power loss, which would be dP dt when the current itself is 11. So I is 11. Okay, so this is sort of everything in this paragraph spelled out into equations, and we're going to use the fact that this is a chain rule problem because you see I is a function of time and P is 8I squared. So if we go to calculate the derivative, I'll do that over here. It will be, okay, well, we bring down the 2I and then it would be to the 1. Okay, we take the derivative of the outside and then times, oops, it should be di dt. So here this was, derivative of the outside function. The outside function is the square, and then leave the inside alone. That's this part, and then times the derivative of the inside function. This is the chain rule. And you see, all we need to do is fill in these numbers that we have, and we will have the rate of change. Okay. When I equals 11, we have the following. We have 16, I, and then this, which is going to be 880. And this would be watts per